Thanks. I'll begin with a word of prayer. Heavenly Father, we again, Lord, thank you for this opportunity we have just to come together, study your creation. I just pray that you'd give clarity today, that the students understand the technique we're covering, and that they'd be able to make it their own. Lord, in your name I pray. Amen. So I asked you guys to try to calculate the integral of the square root of 1 minus x squared dx, and that was mean because unless you remember calculus that you've had from previous instructors, I have not told you how to do this one yet. Like you can, I don't know, maybe, oops, I just pressed a button. Hope it's still okay. As far as I know, you can't do this with integration by parts or the certainly not u substitution. So the method for this is what's called the trig substitution. So what you do is you let x equal to, for example, sine theta. All right, if I let x equal to sine theta, then what's 1 minus x squared equal to? 1 minus sine squared theta, right? So that's cosine squared theta, right? And what's dx? Cosine theta d theta. So with that substitution, this integral becomes the square root of cosine squared theta times cosine theta d theta. So if cosine is positive, and it is, for this substitution, you got cosine squared theta d theta after we make this substitution. And hey, that's not too bad, right? Because we know how to do integral of cosine squared. What's this? Right? Going back to what we did Friday. And so then you can integrate. We get ourselves a theta over 2 plus 1/4 the sine of 2 theta plus a constant. Now this is not the answer, right? The answer should be in terms of x. So for a problem like this problem has what I call a naked theta. And that's just because there's just theta sitting out here on its lonesome. And so that pretty much means that you're going to have to write your answer in terms of an inverse trigonometric function. So I can solve for theta. Theta is equal to the inverse sine of x in this one. And so we get 1/2 inverse sine of x plus 1/4 the sine of 2 times the inverse sine of x. Now the second term I might be able to simplify, but I'm going to spend my energy simplifying later examples, so I'm just going to leave this answer like this here. So any questions? No? Let me show you another example. Suppose we're going to integrate 1 over the square root of x squared plus 9. I don't think that's one of the basic integrals that we found in our study of weird trigonometric functions. But even if it is, forget about that for the moment. How can you do this integral? Well, let's see here. The basic point of this substitution that we just did, right, is to change the thing under the square root to be a square, right? So you think about that. Let me just point out that we have basically 3, so here's some algebraic patterns that we can sample from. All right? So of course there's cosine squared theta plus sine squared theta equals to 1, right? But there's also 1 plus tangent squared theta is equal to secant squared theta, right? So let's see here. Let's look at this a different way. We have cosine squared theta is 1 minus sine squared theta, right? And we also have that, secant squared theta is 1 plus tangent squared theta. I'm just writing it again. Sorry, not to be But we also have tangent squared theta as what? Right. Now, if you multiply this by, and multiply this, and multiply this by a constant, if you look at that, that gives us like a squared cosine squared theta, right? Excuse me, is equal to a squared plus a sine theta quantity squared. This gives me a squared secant squared theta is equal to a squared plus a tangent theta squared. And this gives me a squared tangent squared theta is equal to a squared, a times secant theta minus a squared. So I just put a big box around these. These are like super nice algebraic observations that we can use as we try to tackle the question of how do you integrate things that have square roots in them. All right, that's our goal today, is to try to come to some understanding of how do we integrate things that have roots in them, square roots in particular. So like this is another example. Oh, just to point out, in my first example, what did I do as it relates to the boxed algebra? Example 1, what do we have? Ah! Basically, we had a equals to 1, right? And we are thinking of, this is basically a equals to 1 in case what? I guess I should number these. Case 1, 2, 3, right? That was case 1. We used case 1 of my algebraic observation. So you guys, what kind of substitution should I make this time? How can I convert this to be the square of one thing rather than sum of two things? Cinch. Very good. For tomorrow. No cinches yet. Today I'm doing trig substitution, but I appreciate the comment. How about like it's this pattern, right? I've got something that looks like this. It's a number plus a variable squared. So, just to be clear, this is something like we make x equal to a sine theta for this kind of pattern. Here we make x equal to a tangent theta. For this one, we make x equal to a secant theta. So again, here, if I make x equal to 3, tangent theta, we're good to go. Because x squared plus 9 is equal to what? That's just 9. Oh, I'm an idiot. What am I supposed to do? Oh, no, I'm fine. Sorry, I retract my idiocy for now. So apparently x squared plus 9 is 9 secant squared if we make an x equals 3 tangent substitution here, right? Why do I do that? Because I hate square roots and I want to kill them. Okay, so there's a sufficiently violent characterization of what we're doing. You should remember it. What's the thing you hate the most?
Square roots.
Square roots. Okay, I was getting to that. You jumped ahead of me. It's good. I thought you were going to answer calculus too. It's good. This will pass though, and if you survive, you should survive. And if you do the work, you can survive. You leave here. Well, there's these movies. This guy talks on the phone. He talks about how he has a particular set of skills and all that and stuff. Like that's like for real in here. If you make it through calculus 2, it will change the way you're able to think about math. It's a game changer. It will level you up. What was the square root of x squared plus 9? It's 3 secant theta, right? So this says the square root of x squared plus 9 is equal to 3 secant theta. All right? So I put 3 secant theta here. When you do a u substitution, right, what do you have to do? You have to plug in the formula for u somehow, right? but you also have to differentiate the u and figure out how it relates to the dx. What's the difference between u substitution and what I'm doing right now? Let me just put it up here, right in front of us. How about this? Integral of, e to the x squared times 2x dx. You let u equals x squared, right? You got du is 2x dx. What happens? You're like, integral of e to the u du. E to the u plus a constant, e to the x squared plus a constant. Thank you. A quarter of my first test is done. Woohoo! All right, I'm just kidding. But, this is u substitution. What's the difference between this kind of substitution and that kind of substitution? Like, what's the difference? What's the substituted variable here? What's the substituted variable here? What's the substituted variable in u substitution? It's kind of like asking when's the War of 1812? It's u. Right, it's u. It's u substitution. Trigonometric substitution, what's the substituted variable? Is not x. X is the old variable. What's the new variable? It's the theta. So if we were to write this in the same way we write u substitution, we'd say something like theta is equal to inverse tangent of x over 3. But we don't write that because that's useless. This is an example of what's called an implicit substitution. You're defining the substitution by an equation rather than explicitly. So this is explicit versus this implicit. Implicit substitutions are very powerful. And they're also easier in a certain regard. You notice how we don't have to solve for dx? Right? Like, it's just there. And you plug it in. Okay, then what? Oh, the 3's cancel, right? So we're just left with secant theta d theta, right? If only we had done the integral of secant theta in some previous class. Oh, we did. So this is the natural log of the absolute value of secant theta plus tangent theta. We worked that out Friday, right? Now this one is wonderful. This one does not have a naked theta, like that one. All the thetas are packaged inside trigonometric functions. That means I can write the answer as an algebraic function. What's an algebraic function? It's a function whose formula is given to you by a finite sequence of algebraic steps. Us mathematicians are really, really sneaky in our naming of things, right? Algebraic function is what it sounds like. Now, here, you can draw a triangle which represents the substitution. What was the substitution? It was tangent theta. I'm writing it slightly more suggestively. Tangent theta is equal to x over 3, right? Now, this is related to a whole family of triangles of which they're similar, but I don't know. Personally, I like to put a theta here, and I like to make the opposite side x, and I like to make the adjacent side 3. The awesome thing about these triangles, if you do it right, what's the remaining piece in the puzzle, the one that's not in the one that's not explicit from the substitution in trigonometry, will be whatever it is that you tried to get rid of. So what did I try to get rid of? I tried to get rid of square root of x squared plus 9. It's up here. And how do I know that? Well, experience, but also Pythagorean identity, right? Opposites, this squared plus that squared square rooted, hypotenuse. So then, with this triangle, it's very easy to write down what the formulas for secant and tangent are, right? What are they? So this tells me, like, secant theta is hypotenuse over adjacent, right? It's 1 over cosine, which in this context is the square root of x squared plus 9 divided by 3. And what else? Oh, tangent theta. I guess we already know that, right? So then you put those over here, and there you go. That's your answer. Natural log, the absolute value of the square root. I guess we could simplify it a little bit. You guys tell me how. Yeah, we can simplify our answer a little bit more using, here, I'll make one more step. This is the natural log 1/3 times the absolute value x plus the square root of x squared plus 9. Sorry, energy low all of a sudden. I don't know why. Anyway, there. You got a log of a product. So what can you do with the third? This is a pretty good answer. I'm working my way towards a slightly better answer, okay? So this is log of 1/3 plus the natural log of x, absolute value rather, absolute value of x plus the square root of x squared plus 9 plus a constant. So what you can do is, this is just a number, right? So you can just lump that into the constant, and a good answer is this: natural log of the absolute value of x plus the square root of x squared plus 9 plus a constant. There you go. That's a, I don't think anybody can argue with that answer. That's a fine answer. Es bueno. Now, Dr. Scambordis told me of this problem. He said it was amazing. I must try it. 8.3, number 6. I will share with you all the joy of section 8.3, number 6, I think. Well, maybe 8.4, number 6. 8.3 we already did Friday. 8.4, number 6. Yes, here we face the integral of x squared divided by the square root of x squared minus 4. All right. Just making sure I copied it down wrong. I tell you, the worst thing is to copy a problem down wrong and not realize it. Anyway, so you've seen case 1 in action, our first example. You've seen case, what is this one? Case 2 in action over here. And this one actually fits this pattern, right? It's like the variable squared minus the constant squared. So this suggests we make an x equal what substitution? Yeah, 2 secant theta substitution. All right. All right, so with that substitution, x squared minus 4 is equal to 4 secant squared theta minus 4, which is, by the way, 4 tangent squared theta. And so the square root of x squared minus 4 is just 2 tangent theta. Well, that's nice. What's dx? If you didn't know the derivative of secant before, you'll know it after this section, that's for sure. You can't miss it. So the derivative of secant, secant tangent. And all right, so put it in. We've got 4 secant squared theta from the x squared. I got myself a dx, 2 secant tangent. And I divide by 2 tangent theta. Oh, cool, the tangents cancel. Oh, not cool. Not cool at all. That is 2, oh, ow, oh, ow, ooh, ooh, ow, 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 ooh, ow. That one hurts a little. Let's see here. Put a 4 out front. Do you remember the secant cubed? We did that last class. It's almost like we cover the section before this one so that you can understand this section better, isn't it? It's like math builds on itself. Like, failing to study a section before can hurt you for the rest of the course. Yeah, it's true. It's all true. Everything I said is true. Well, up until, I mean, there's some places where we kind of break the story and what you don't know about integration doesn't hurt you for a while. But there's always the final. So, anyway. I don't really want to do integral of secant cubed again today if I can help it. Can you guys tell me the answer? Please, please, please. Pretty please. I can try to remember it, but I don't think that's going to go well. I remember that there's a natural log of secant. Thank you.
Secant theta tan theta.
Okay.
Plus 1/2 the natural log of secant theta plus tan.
Fantastic. Thank you. And that all gets multiplied by the 4 in this problem, right? So we have to take care of that. Let's see here. I'll clean this up a bit. So we got 2 secant tangent plus 2 log of secant theta plus tangent theta plus a constant. All right. Again, this problem is very nice in the sense that after we make the trigonometric substitution and do the integral in the trig function, we're left with something where there's no naked theta, right? So there's just theta wrapped in trig functions. So those can be converted to algebraic functions. So I can draw a triangle here again, like we did for that problem. And we can convert functions of theta to functions of x on the basis of the substitution. So let's do that. Let's see here. What's my triangle for this one? I've got secant theta is equal to x over 2, right? So I'm going to think of that as the hypotenuse over the adjacent side, because I remember that secant is 1 over cosine. So it's the reciprocal of adjacent over hypotenuse, right? And so that suggests that I put an x for the hypotenuse, and I put a 2 for the adjacent side in this here right triangle, which this is just a graphical representation of the substitution, right? So what's the missing link here? What's this guy? See, it's exactly the thing we tried to get rid of again. Not an accident. And of course you can check that. This squared plus that squared gives you what? 4 plus x squared minus 4, which is x squared square root x. Of course, this substitution assumes that x is so chosen as to make the as to be positive. You know, otherwise the substitution breaks down. But okay, so then we can. What's tangent theta then? Basically, that's the only other thing I need to know here. What's tangent theta? Opposite over adjacent, right? So x squared minus 4 over 2. And so put it all together, what we get? We get 2. Secant theta was what? X over 2. Tangent theta, square root of x squared minus 4 over 2. And then plus 2. 2 natural log absolute value secant theta is x over 2. Plus the square root of x squared minus 4 divided by 2 plus a constant. I'll write another step here. So this is 1/2 x square root of x squared minus 4 plus twice the natural log of the absolute value of x plus the square root of x squared minus 4 minus 2 natural log of 2 plus a constant. Because again, we've got a common half in both of the things in the log, so I can use the properties of logarithms to, you know, I've got division by 2, so that's the same as minus the natural log of 2, right? If I've got the natural log of Pac-Man over 2, that's equal to log Pac-Man minus the log of 2, right? Property of logs. So I'm using that here. It's just that there's a 2 that multiplies as well. Why do I do that? Just to point out that the 2 log 2 can be lumped into the constant of integration, right? And so here's a nice answer. 1/2 x square root of x squared minus 4 plus twice the log of the value of x plus square root of x squared minus 4 plus a constant. And there you go. That's a nice answer, I think. Now, honestly, I will freely admit that what I had up here is almost a nice answer. I mean, if you wrote that on the test, for example, I wouldn't take off much. Not much at all, really. But, you know, if I say simplify your answer in terms of algebraic functions, then this is the optimal answer, pretty much. Now, if you felt strongly about the 2 going inside and making that a square, I wouldn't quibble. I'd be cool with that. But the point is some appreciation of the fact that you can simplify the division by 2. That's the main feature there that distinguishes those 2 answers. Confidence and understanding of rules of logarithms versus not being aware of them. Right? So like on the test, or just in life, you don't write this repeatedly on a paper. Like that, you don't, no, we do not do that. If we have the square root of 25, we do, this is 5. Okay, because in this, square root of 9, like this does not stay like that. You write 3, right? So what I'm trying to encourage you to do here is think. You can think, right? I know you guys can think. I am not talking to most of you, but there's a specific subclass of you who, for reasons I don't entirely understand, like put off doing elementary arithmetic till some future date when never comes. So I get answers that involve like sophisticated techniques of integration, right? Like you're doing trig substitution or integration by parts, several fold in, but your answer has like the square root of 100. It's not healthy. You should write 10. Just saying. Anyway, I don't take a lot of points off for that sort of thing. I'm just trying to encourage you guys to be more professional in your mathematics, that's all. So most of you want to be engineers, right? So you want to be, you know, good at math, right? Yeah.
I misread the negative 2 natural log.
Excuse me. That's because the natural log of x over 2 plus the square root of x squared minus 4 divided by 2 is equal to the natural log of 1/2 times, you know, x plus the square root of x squared minus 4, right? And so this thing we think of as like Pac-Man,
Right.
in my comment over there. It's okay. Sorry. I would say I will stop coughing, but I really can't promise that. I wish I could promise that. Other questions? Okay, so those are your 3 main cases, right? If you think about it, what else can happen with a quadratic? If you've got something under a square, right? That's pretty much it. Sum of 2 squares, a difference of squares, one way or the other. Those are your 3 cases, right? Shall we try another? Let's try another. Let's see here. Stupid. Let's see here. What if I had something like the integral of dx over x squared plus 6x plus, I don't know, 9, no. 13 there. Now that's not good enough. Let's make this let's square that thing. Now this technically, I've kind of broken ranks here at the point. I mean, there's no square root in this problem, right? But this is also amenable to a trig substitution. Basically, the point is you can make the denominator rather, just a single thing rather than a sum of three things, then maybe you can fix it, right? So the way we do this is, first of all, we use this thing called completing the square. Remember completing the square? So here we go, x plus 3 quantity squared plus 4, because 9 plus 4 is 13. All right. So now I think about, okay, well, I kind of know u substitution's not going to help me out here, right? But you might have been able to do this one before we had this. Well, I don't know. Maybe not. Let's see here. I think I want to make a. Let's see here. How about if I make an x plus 3? If I make x plus 3 equal to 2 tangent theta, I think that ought to do it. See, because then x plus 3 quantity squared plus 4 is what? I believe that's going to be a 4 secant squared theta, right? Because tangent squared theta plus 1 is secant squared, right? And so with that substitution, this integral here becomes what? What's dx? Well, derivative of 3 is 0, right? So dx is just equal to 2 secant squared theta d theta. And what we got is we got 2 secant squared theta d theta. And let's see, the thing that's squared downstairs becomes 4 secant squared theta squared. Well, that's a little bit unpleasant, right? Kind of scary, isn't it? It's a little bit scary. Don't worry, though. We'll get it. Let's see here. So that is 2 over 16, and the integral of d theta over what? Secant squared theta, right? Because this becomes secant squared theta over secant to the 4th theta after you do the algebra there, right? And that reduces to 1 over secant squared. But hey, what's that? That's cosine squared theta, d theta, of course. Don't forget the d theta. And that, of course, is 1/16th integral of 1 plus cosine 2 theta d theta, which we can do. And then, of course, you have to unwrap the substitution, right? You go back up to the top where we made the substitution. And this gives us that theta is inverse tangent of x plus 3 over 2. The theta is naked. I don't really have much hope of eliminating the inverse tangent here, so the triangle won't help me much. Inverse tangent of x plus 3 over 2 plus 1/2 the sine of 2 times inverse tangent of x plus 3 over 2 plus a constant. And there you have it. I mean, obviously, if you differentiate this function, you get back that, right? No, I think we're actually to the point where it's, you know, it might be harder to differentiate that and to show yourself that it is the integrand than it is to do what we just did. Checking the answer might actually be harder than finding the answer here. Es bueno. Let's see here if I can find another good problem to do. Any questions? So you guys understand which one you want to make? I usually get a slew of questions like, how do you know which substitution to make at this point? So I tried to head that off at the pass by emphasizing these are the patterns, right? Basically, if you see a square root, then you want to think about these, right?
How do you know, like, between 1 and 2? A squared plus quantity squared.
Oh, that's a typo. Oopsie. That's a very, very good question, sir. What's your name?
Paul.
Paul, thank you. Yeah, that's supposed to be a minus, right?
The third one, secant theta squared.
Oh, yes, thank you. Also, that's a very good comment, thank you. I do make mistakes. Mostly I'm trying to get you guys to talk, yeah. These are all on purpose, of course. Yes?
Simplify that more?
What's that?
This question over here, can we simplify that more?
That, possibly.
Because the book has,
Possibly. I mean, here's the game we can.
as the,
Here's the game we can play. So the sine. Oh, this works. Every once in a while it works. Let's see here. The sine of 2 theta, right? Well, sine of 2 theta is 2 sine theta cosine theta, right? So this, in terms of the triangle here, I mean, you can't, I didn't bother because, like I said, x equals sine theta, right? So that means that x over 1, so the hypotenuse is 1, the opposite is x. Here you got your square root of 1 minus x squared. So you got 2 sine theta is x, cosine theta is square root of 1 minus x squared, right? So, so yeah, you could simplify this answer as 1/2 inverse sine. Nathan, is it? Thank you. Yeah, this is a comment worth making. Thank you. So that's really 1/2 x times the square root of 1 minus x squared. Now do I have the book?
I think so. You have
An extra x.
half times the square root of 1 minus x squared, I think.
Whoop. Whoop.
Let me make sure I got that right.
Whoop. Did they factor the half out front? I mean, there's a half to, but you
Yeah,
you can,
well, the half was there. So.
is it right now? I hope it's right. But yeah, we could do that. The thing is, the reason I didn't do that to start with is because there's just nothing I can do about this inverse sine, right? That's there, you can't fix it. You know. Similar things can be said over here. You could simplify this to what? This term right here could be simplified to the half, right? So this is really just, this could be simplified to sine theta cosine theta, which in this context would be equal to, did I erase the thing? Oh, I haven't drawn it yet. Let's see here. If this is theta, tangent theta is x plus 3 over 2. And so this guy would be 2 times x plus 3 over x squared plus 6x plus 13, which is kind of cool. So, I mean, yeah, that's an improvement on that answer, I will admit. So, I do welcome your comment. Anytime we have a sign of 2 things, we can use this identity to simplify it, right? That is true. All right, let's do a sort of an applied problem to finish class today. Tomorrow I will show you guys how this is not always the best way. All right. For example, tomorrow I will show you if you look at the integral of the square root of 1 plus x squared dx, right? If you look at that example in terms of trig substitution, you know what it gets you? Which I mean, you can kind of just work it out without writing. Which we would let x equal what? Tangent, right? So that would simplify to secant. The square root simplifies to secant. The dx simplifies to secant squared d theta. That, under a trig substitution, is integral of secant cubed. I don't know about you. I try to avoid secant cubed when I can. All right? So, is there another way to do that besides trig substitution? There is. There is a corresponding triple of hyperbolic substitutions we can make. And those hyperbolic substitutions are often easier than trig substitutions, and vice versa. There are problems which are easy in trig substitution that are hard in hyperbolic, and vice versa. So they're kind of two different sides of the same coin. And I'll show you that tomorrow, the hyperbolic substitutions. And I'll answer questions about trig substitution if you got any, if all goes as planned. But here's an example. Let's try to find the area. I guess this is problem 44. You're asked to find the area of this shaded region. So here this height is h. And this is radius r. So let's see here. What would that be? This point here is what? Ooh. I guess I could look at this as being theta, right? That theta would be equal to what? Oh, I'm sorry. Let me stop that. I mean, we could figure that out, but I don't. It's not actually what I want to do. Let me hold off on the triangle here for a second. First of all, what would the area equal to? We do integral. What's the equation of this? X squared plus y squared equals r squared, right? So we have to integrate, y. Excuse me. So let me draw a typical thing we're adding up. Here's our little dA, right? So dA is equal to y minus h dx, right? And so we've got square root of r squared minus x squared minus h dx. From where to where? How do you figure this out? We need to figure out these intersection points, don't we? Let's call this thing A, let's call this thing B for lack of imagination. Integration from A to B, right? There's a symmetry here we can exploit, right? So why don't we just trade this for 2 times the integral from, say, 0 to b of the square root of r squared minus x squared minus h dx, right? Surely we can do that. And you know what? While we're at it, why don't we just do that integral of h and just get it over with? What's the integral of h? Yeah, well, no. H is a constant here. H is a given constant. The integral of h dx is just hx. It's h times the length of the integration region. We have just 2hb from that term with a minus. So minus 2 times the integral of the square root, r squared minus x squared dx Again, from 0 to b.
H, 2H.
See? Keeping you guys, keeping it interactive. That's what I do. Okay, sorry, I'll try to stop scheming. What is b? I mean, you can figure it out from this triangle, right? So we have h, the radius r here, right? And this is b. So b is equal to what? Right? So b is actually the square root of r squared minus h squared. All right, now at long last, I'm gonna stop writing all this and just focus our attention here on this piece. I'll do it over here. How are we going to do that integral? How are we going to integrate from 0 to the square root of r squared minus h squared, the square root of r squared minus x squared dx? What should we do? I propose we make an x equals r sine theta substitution, right? You could use cosine theta if you want. I'm going to use sine theta. Now if I do that, right, dx is easy, right? And the square root of r squared minus x squared is what? It's our cosine theta, much for the reasons we did before. But what's new here? This is a definite integral, right? So we have to change the bounds. How do you change bounds for an implicit substitution? I think the simplest answer I can give you is as common sense dictates. So x equals 0 is r sine theta implies theta equals what? How can you get 0 from sine theta? Put theta equal to 0, right? And if we want the square root of r squared minus h squared, right, equal to r sine theta, well, that says that apparently theta should be equal to inverse sine of the square root r squared minus h squared divided by r. I mean, that's not the greatest. Let me call that theta 1. Ah! Shut up! No, no, no. All right, I'm almost out of time here. I'm gonna wrap it up though. So this is what then? 0 to theta 1, right? Where this is theta 1, and this is what? R squared cosine squared theta d theta. So that's what? We just worked that out over there, right? But well, I guess not. Anyway, so here we go. R squared over 2. Excuse me. Theta plus 1/2 the sine of 2 theta evaluated from 0 to theta 1. And let's see here. We said 1/2 sine 2 theta is what? This is, we can rewrite this as what? We can rewrite that as sine theta cosine theta, right? And of course, you plug in 0, you get nothing. The upper bound gives you theta 1, so we get 1/2 r squared theta 1 plus sine theta 1 cosine theta 1. Now I could, let's see here. So let's see here. What's the substitution? The triangle for this one, theta 1. R is the, excuse me, R is the hypotenuse. Thank you. Square root of, thank you for that. R squared minus h squared. And so down here you got h squared, right? And so this simplifies to 1/2 r squared inverse sine of the square root of r squared minus h squared over r plus the product of sine cosine, which is, in this case, h squared, square root of r squared minus h squared divided by r squared. And there you have it. That's the area. Oh, thank you. Very good. Otherwise, it would be dimensionally inconsistent. What happens when you put h equal to 0 here? This is gone. This becomes the inverse sine of r over r, otherwise known as inverse sine of 1. What's the inverse sine of 1? Pi over 2. 1/2 r squared times pi over 2. In other words, what do you got? Pi r squared over 4. Hey! Oh, but you still got to go back over here. Oh man, that's just the answer. That's not the answer. I'm an idiot. We got to take that and plug it in over here. And then that picks up a 2, which then gives us pi r squared over 2. Anyway, I'm sorry if I've messed up a detail here, but I wanted to show you how to do that. That's problem 44 in the homework. This always gives you guys trouble. But the important idea here really is this triangle and changing to figure out how the h and the r relate to what the x bound is. It always throws students for a loop. Anyway, thanks guys. Oh, or not. This has to go over into here, and then that's the answer. Okay. Yeah. Where the b is this. Yeah. Why did I do this problem? What's wrong with me? You can hit the record. Thanks.